So today is December 3rd. Again, if someone next to you doesn't have a phone, please share. And again, no, I am going to go kind of fast, and you can pause this video and rewind if you need to. We have some do nows here. CP81, quite a few problems here. These are graphing, 12 through 28 and 29. Label the vertical asymptote, horizontal asymptote. I don't know if you need an x-intercept or not necessarily. But label is what you need to do. So first and foremost, what is domain? What is the domain of this? Well, domain, denominator, domain. So we always want to factor first. Rule number one, we're graphing rational functions today. Factor first. It's going to tell us so much information about the graphs. And so -6 would be a -3 and a +2. And from those bubbles, we can see the domain x cannot equal +3 and x cannot equal -2. This is the domain. All the other x values work. But when we talk about rational functions, and this is rational fractional, you can see we have a fraction here. They create some other interesting graphical anomalies. So we had things like multiplicities and that sort of stuff we were talking about before, but now we're talking about rational fractional functions. And a rational function, which I'll say is R for rational in terms of x, is that we have some polynomial on top, I might call it n of x, and some polynomial in the denominator. And so there's examples in your books about all kinds of things that might represent a rational function, like 2 over x minus 1. This is a rational function. Up 2 maybe is a polynomial. And x minus 1 certainly is a polynomial. Or even something like x cubed minus 8 over x plus 4 is a polynomial over a polynomial, and therefore it's a rational function. Well, anytime we're dividing, we're going to create instances where x causes an undefined value. And graphically, that's also going to cause what's known as a vertical asymptote. So VA stands for vertical asymptote. And an asymptote is a thing that you can't touch. It creates basically a blank spot in the graph where nothing happens there. So we have these vertical asymptotes, and you can kind of see these graphs are crazy graphs. If you wanted to graph this in your graph calculator to get an idea, you do need to be careful with these functions and make sure that you put your denominator in parentheses. But we have, let's see, x squared divided by the entire x squared minus x minus 6. So make sure you get the whole denominator in parentheses, and then when you go to graph, you can see it's a crazy function. But you'll notice at -2, if I trace and type in -2, trace -2, you can see there's actually no y value there. It's literally undefined, not defined there. And you can see at -2, you can see the graph. One portion goes up here to positive infinity, and this other portion of the graph goes down to negative infinity. We would say that the graph diverges at that vertical asymptote. There's another vertical asymptote here when x is 3, and you can see that's another place where the graphs sort of veer off in different directions. So then what's a horizontal asymptote? Well, a horizontal asymptote is slightly different. A horizontal asymptote technically is what happens to our y values or to our function f of x. What happens to the y values as x gets really large? Really large, i.e. 1,000,000, or a trillion, or a gazillion, or really as x goes to positive infinity, or as x gets really, 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 really small, like negative 100 or negative 1,000, or really if it goes all the way to negative infinity. So a horizontal asymptote is slightly different than a vertical asymptote. A vertical asymptote we will never, ever, ever touch. But a horizontal asymptote does very, very weird things. And it really only describes what happens for x values that are really large, like positive infinity or negative infinity. So around 0, it doesn't tell us much. Let's see how we do this. So example 1, graph the rational function. Label the vertical asymptote, horizontal asymptote, and an x-intercept. Well, we can do that pretty easily for some of these. So today we want to be able to distinguish between a function, a rational fractional function that's in lowest terms, and a rational fractional function that's not in lowest terms. And so this, you'll notice this is the only x we have. I can't clean it up at all. You can compare that to these functions here. You can see we've got x squared, we've got x. This is really, it could be reduced. And we're going to talk about how to do that. So first of all, I can find domain. Denominator, domain, denominator, domain. So we know that x cannot equal 0. And because that comes from the denominator, that happens to also be my vertical asymptote. X equals 0. And that's something I'm going to graph. So I can graph that. X equals 0 is a vertical line through 0 on the x-axis. So we get this dotted line. And there is our vertical asymptote, x equals 0. I use a dotted line to represent all of my asymptotes. And then, because this function is in lowest terms, like I can't divide, I don't have x's top and bottom that I can divide out. It always happens to have a horizontal asymptote of y is equal to 0. So that's another thing I can graph. So y equals a number is a horizontal line. And what we've done is sort of created our graph. It's in 4 little regions here. And they want us to find the x-intercept. Well, an x-intercept occurs when y is equal to 0. So I can find an x-intercept pretty easily here. So y is equal to 0. So we would have 0 equals 1 over x. If I cross multiply, because that's how I would solve this, 0 times x is 0. Does 0 equal 1? No, it does not. So there is no x-intercept in this particular case. But that's how you would solve it normally. You could now, I need some points on the graph, and anytime I need points on the graph, I can very, very easily just make a little XY chart. And I'm always going to choose x values to the left and to the right of my vertical asymptote. So maybe -1 and +1 are good values to plug in. So if I plug in for x, 1 over -1, well, that's just -1. So I have the ordered pair, -1, -1. And then for the other side of my vertical asymptote, I can plug in a +1, 1 over 1, just equals 1. So I have 1, 1 as an ordered pair on the graph. So I could plug in additional values if you wanted to. You could plug in 2, you could plug in -2, and I'd get 1/2 or -1/2. And what really happens here is the graph just creates this little L shape where it's just approaching our little asymptotes. You guys have graph calculators, use them. So you can absolutely use your graph calculator. This is the parent function, the most basic rational function, the inverse function. And so all of our little lowest terms functions are going to kind of similar to this, where you have sort of this L shape in the one corner and again, another sort of L shape in the other corner. So definitely double check your graphs. You can use trace, and I can type in my x value of 1, and you can see you get output of 1. If I type -1, you can see I get -1. So use trace to help you graph. I really like to see your asymptotes labeled and at least one point labeled as well. All right. Again, we have a plain old number on top without an x. This function is in lowest terms. And so I'm going to start by thinking about domain. Domain comes from the denominator. I'm going to factor first. So when I factor, I can take out an x. Factor first if you can. We have x minus 2 left over. So I can see the domain. X is not allowed to be 0, and x is not allowed to be 2. That means that we have actually 2 vertical asymptotes here. 2 things where our graph is going to diverge. Kind of interesting. So I'm going to go ahead and just graph those. Okay. So x equals 0 is our vertical asymptote right through the origin. X equals 0. And then x equals 2. Now again, since we are in lowest terms, I'll show you what to do when we're not. Our horizontal asymptote is going to be y equals 0. It's really like you wouldn't be able to divide this, which we'll talk more about tomorrow. So I get y equals 0 for our horizontal asymptote. You can see we've basically split up our graph into 1, 2, 3, 4, 5, and 6 sections. We're going to fill up about half of those sections. Again, I could try to find the x-intercept by setting y equal to 0. But again, if I tried to do that, I'd cross multiply. 0 times this denominator is 0. So again, there is no x-intercept. So instead, I have to resort to other means. I'm just going to do a little table of values to plot a couple of points. Again, you need to choose values to the left and right of every vertical asymptote. So here at 0, my x value to the left I could use might be -1. To the right might be +1. And I have another vertical asymptote. I already used +1. To the right of 2 would be 3. So I have a few good values to plug in. And let's see, I can plug those in pretty easily. -3 over 1, -1 times -1 is 1. Actually, it's easier to plug them in here. That would be -1 times -1 minus 2, so that'd be -3. So I'm going to get -3 over +3, which is -1, -1. If I plug in a 1, I have -3 in my numerator, 1 for the first thing, and then 1 minus 2 is -1. It's always easiest to plug things in factored form. So that's just going to be -3 over -1, which is +3. So 1, 1, 2, 3. And then if I plug in a 3, -3 is on top. I have a 3 at the bottom there, and 3 minus 2 is 1. So -3 over 3 is -1. So 3, -1. Now, because I've been doing this for 20 years, I happen to know that this function, again, gets close to this L shape here. In the middle, it's probably a parabola type shape. And then here, again, we just approach those asymptotes. This is definitely something you'd want to check in your calculator, so please don't be shy. I've been doing this for 20 years. It takes a long time to figure out what these sort of look like. But there you go. So you can see we've got that sort of L shape down here. We've got the parabola shape in the middle, and then another L shape on the right. are, these are not in lowest terms. And you can see that we've got x's on top of them. You can imagine that they could be reduced. Like we could actually do some division and clean up these fractions and make them into the lowest term. But I'm going to show you a shortcut for that. I can't factor this, so I know that the domain is x cannot equal -3, which means I have a vertical asymptote from that at x equals -3 that I can graph. So do that. 1 to -3. The vertical asymptote right there. I'm going to label it. Now, for the horizontal asymptote, this is a great method, excuse me, for figuring out those horizontal asymptotes. And the reason I like it is because you're going to see this method again in calculus. And what we can do is, we got lots of x's going on here. So we're going to divide through everything by x. There's lots of x's going on, so we can do that. And that's going to rewrite my equation a little bit. So I have a function, x divided by x. And here we're going to have x divided by x plus 3 divided by x. Now the rule is you have to divide everything by x. Okay. And well, then if I were to do that, this little complex fraction I've created kind of cleans up really well. And so, well, x divided by x, that's always just 1. And here, x divided by itself, a number divided by itself is 1. And then 3 over x doesn't clean up. So what we're going to talk about is what happens as x gets really large or really small, because that's what horizontal asymptote means. So what happens as our x values gets large, really large? So let's say, let's start with 10. 10 is a pretty big number. 3 divided by 10, well, that's 0.3. Okay, that's interesting. What about 3 divided by 100? Well, that's 3/100ths, right? And if you think about taking a unit that's, maybe 3 centimeters long, and you're dividing it into 100 pieces, those are pretty small little pieces, right? So we're getting really small little parts here. We're getting 3 out of 100 different little pieces. Well, now imagine, what if that x is 1,000? So we take that 3 and we're now dividing it into 1,000 little pieces, and we want 3 of them. Those are even smaller pieces. So we have an even smaller fraction. And well, if we divide that unit into 1,000,000 now, let's divide by 1,000,000. Well, that's 3 out of 1,000,000. 3 of those millionth little pieces. So 3 little millionths of a unit is really, really tiny. And in fact, as x gets really, really large, as we go to infinity, imagine taking and cutting it into an infinite number of pieces. Well, those pieces are now infinitely small. They're infinitely small. And so if we take a number and we add 3 of those infinitely small little pieces, they're so infinitesimally small that it's really like adding nothing. And so this is what we say, that as x gets really large, this fraction becomes infinitely small. And so it's negligible. It's not going to do anything. And so what we're left with is 1 over 1, which is just 1. So our horizontal asymptote turns out to be 1. Y equals 1. And the same thing is true if we go to negative infinity. So again, if we went to negative infinity, well, we're negative infinity. I'm still cutting my unit into an infinite number of pieces. We're going in the other direction, so we're subtracting an infinitely small little piece. Well, it's so tiny, it doesn't even matter. So we still get 1 over 1. 1 minus nothing is still just 1. And so that's how we get those horizontal asymptotes. Let's see. I need some x and y values. We can actually find x-intercept. An x-intercept occurs when our function is set equal to 0. So let's see what happens for this one. We're going to solve here. Ooh, cross multiply. 0 times my denominator is just 0. So I get an x-intercept of 0, 0. Right there. So that's a nice little point on my graph. So I have a point to the right of my vertical asymptote. I need a point over here. So I'm going to plug in maybe -4. So I'm going to plug in -4. -4 is on top. -4 plus 3 is -1. So I get 1, 2, 3, 4. -4, 4. I'm imagining there's L shapes here, so it looks something like this. And again, you have a calculator, use it. So I have x divided by, don't forget the parentheses, x plus 3. Cool. So you can check, use a trace. So if I type in -4, I get my output of 4. If I type in 0, I get my output of 0. And you can, check 10. Oh, it's 0.7. It's getting close to 1. If you were to check larger values, you could see they get even closer and closer and closer to 1, but never quite touch 1. All right. Denominator domain. So I know right off my denominator x can't be 0, which gives me my vertical asymptote. Now, to find a horizontal asymptote, I see I've got these x squared that seem like they could clean up. So I'm going to divide everything by that x squared. Let's see. So if I do that, I'm going to divide the 4 by x squared as well, and denominator by x squared. And clean it up. So x squared divided by x squared is 1. I don't know what 4 over x squared is. Talk about that. And x squared divided by itself is 1 again. So again, we're thinking to find a horizontal asymptote, what happens as x is really, really large or really, really small. So here we're taking a super large number and making it even larger by squaring it. And if we take a number and divide it by a huge number, dividing it into an infinite number of pieces, those are really, really teeny tiny parts. And so it's, again, approaches nothing, all right? It's like adding or subtracting nothing. So we're left with 1 over 1, which is just 1. And plot those. X equals 0 and y equals 1. It's my asymptote. X-intercept, let's see. In the x-intercept, I'm setting my function equal to 0. Cross multiply. Really, anytime you want to find an x-intercept, turns out it just comes from whatever the numerator is. That denominator is always going to cancel out. Since cross multiply, it just comes 0. And this, I can add 4 and then take a square root. So we get plus or minus 2. So I have 2, 0 for an x-intercept and -2, 0 for an x-intercept. Oh, this is a totally interesting function. I don't know what this looks like. I'm going to grab it. I want to make sure I put parentheses in my numerator, so I have x squared minus 4. I have an idea of what I think it looks like, but I just need to double check. Funny. It matches, it doesn't have a button. We have these L shapes, and they're just sort of approaching those asymptotes. Kind of interesting. And again, you can use trace and type in 2, and you can see that it's 2, 0, and -2, and again, you get another 0 there. And all these just get close to 1, which is kind of interesting. So take your time with this. This is kind of weird. Use your calculator to help out. Vertical asymptotes are always going to come from a denominator, and horizontal asymptotes, you're going to clean up a little bit. And when you pick points, choose a point to the left and choose a point to the right of every single vertical asymptote. You're going to be able to do this by hand, but use your calculator. Make a guess first, and then use your calculator to confirm. All right, so go for it.